So I think we can get started. Thank you everyone for coming. I have a lot of material to cover today, and I'm happy to answer questions afterwards, but as a courtesy to the next speaker, if we're getting towards the end, I'm happy to answer questions outside. So my name is Taylor Getz. I work at Hortonworks. I'm the PMC chair of Apache Storm and an ASF member. I'm also involved in a bunch of different projects at Apache, so I kind of think of myself as an Apache guy. So before I get into what's new in Apache Storm and where we're going in the future, I'm going to cover a little of the history. So in Apache Storm 0.9.x, this is when Storm moved to Apache, and that's when we created the first official Apache release. During that line of releases, that's also when we became a top-level project at the ASF. We moved from 0MQ to NETI for interworker communication. That was partly because 0MQ had licensing that was not compatible with the Apache license, and the NETI replacement was also much faster. We also expanded integration. We included connectivity for Kafka, HDFS, and HBase. Prior to that, especially with the Kafka integration, the Kafka integration was a separate project. And as Kafka versions changed, the Kafka spout got forked and modified by a bunch of people, and it became very difficult for people to understand which version to use with which version of Kafka. So what we did was pull that in to our distribution so that we had a definitive source for that integration with Kafka. We also started to address dependency conflicts with user code. It was a start. We didn't get there, but later on we continually improved on that. The Apache 0.10.x releases were all about enterprise readiness. The major feature added in that line of releases was security and multi-tenancy. If you look at perhaps like some of the Heron improvements or the Heron problems that they identified with Storm, we knew about those at the time. But for us to allow enterprises to adopt Storm, we really needed to address security first. And that was a major effort. So we addressed that first. In 0.10, we also enabled rolling upgrades, so you can upgrade from a 0.10 release to another release with zero downtime. We also added Flux. Flux is a tool that allows you to declaratively wire together topologies and do that in a separate YAML file, so you don't have to repackage and redeploy your topology jar in order to change the wiring. So that allows you to have versioned configurations for example, dev and prod. And we also added partial key groupings, which is another grouping similar to fields grouping, but it allows you to spread out the load a little bit more. We also improved logging in 0.10 by moving up to, or converting over to Log4j2. We added streaming ingest into Apache Hive. We added Azure Event Hubs integration, a spout, and then bolts and Trident State for writing to Azure. We added Redis integration and also JDBC integration. So Apache 1.0, which came out on April 12th of this year, was all about maturity and improved performance. In 1.0, we added Pacemaker, which is a heartbeat server. Pacemaker replaces Zookeeper for heartbeats. Pacemaker is essentially an in-memory key value store, and since heartbeats in Storm are ephemeral, there's no reason for us to have to spill them to disk and wait for the synchronization of the Zookeeper quorum. So that allows for scaling to clusters on the order of 2,000 to 3,000 nodes. Pacemaker is also secure, like the rest of Storm, the security features we added in 0.10. It supports Kerberos and also digest authentication. So compared to Zookeeper, Pacemaker uses less memory and less CPU, and there's no disk, it's all in memory. So you're spared the overhead of maintaining consistency, or you're spared the overhead that Zookeeper has of maintaining consistency. We've also added a distributed cache API. So typically, before the distributed cache API, users typically bundled the resources required by their topology, like dictionaries, machine learning models, geolocation data, that sort of thing, in their topology. So that data was static. So that's fine for small files, but large files negatively impact the amount of time it takes to start up a topology. And like I said before, they're immutable, so changes require repackaging and redeployment. So what the distributed cache API allows you to do, it allows for sharing of files, which are stored as blobs, among topologies. And you can update those files from the command line and have your topology automatically pick up those changes. It allows for files from several K in size to several gigabytes in size, and those files can change over the lifetime of the topology. It also allows for compression. So now, instead of having to redeploy your topology when your resources change, you can just update the resources and have your topology pick those changes up. There are two implementations of the distributed cache API. There's a local file system blob store. That's useful if you're not using HDFS. But if you do have HDFS in your stack, then there's an HDFS blob store as well. So the local implementation supports replication factor. So you can say, okay, I want this, when I upload my resource, I want it replicated among supervisor nodes within the cluster. That's not needed for HDFS-backed implementation, obviously, because HDFS already has replication. And both implementations support access control lists. So you can secure them and specify which users have what rights, read, write, that sort of thing. So I don't have a laser pointer, but to create a blob, there's the Storm blob store command. And in this instance, we're creating a file, naming it dict.txt, and setting an ACL and a replication factor. So that will upload the blob to the blob store. And then in order to make it available to a topology, you add some parameters to the storm jar command when you deploy your topology and tell it what key your resource file is named, what the local name. So when the topology comes up, it will automatically download that, and the local name allows you to specify what the name of the file is when it's downloaded to the worker. And then you can also tell it whether or not that resource is compressed. So if you want it to uncompress a file, you can tell it to do that, and it'll decompress the file when it downloads it to the worker. Another new feature in 1.0 is high availability Nimbus. So prior to HA Nimbus, Nimbus was what I usually call a soft point of failure. So if you lost Nimbus, your topologies would continue to operate and process data, but if there was a failure of a worker or a supervisor, Nimbus wasn't around to reassign the work. And also, while Nimbus was down, you wouldn't be able to submit new topologies to the cluster. So with HA Nimbus, what you do is you run multiple Nimbus daemons. And through Zookeeper, Nimbus will do a leader election and figure out which Nimbus is leader. And then when you submit a topology, it will figure out which one's leader and submit it to that topology, or to that Nimbus. If the leader fails, then leader election will happen again, and a new Nimbus will be elected leader and take over. So you will not have any downtime. You'll still be able to submit topologies, and if there are supervisor or worker failures, they'll be able to pick up and continue working. So HA Nimbus increases the overall availability of Nimbus. You can have Nimbus hosts join and leave the cluster at any time. It leverages the distributed cache API for distribution of your topology jar, configuration, and serialized topology. So those get uploaded to the distributed cache and replicated to guarantee the availability of all the files necessary to run your topology. We also added native streaming windows. So streaming windows allow you to specify a length or a duration of how long you want that window to be. So let's say you want to do an aggregation over the last 5 minutes of data that you've seen. You can do that by specifying duration, 5 minutes, or a tuple count. Then there's a slide interval, and that allows you to specify how often you want the to advance. Right now we have two types of windows. We have sliding windows. With sliding windows, windows can overlap. So as the window advances, it's possible to have tuples from the previous window in the new window. The other type of windowing we support is tumbling windows. And in this case, when a window advances, it's a completely new set of tuples within that window. So windows do not overlap with tumbling windows. So for streaming windows, we support a number of different timestamps, mainly because event time is important versus processing time. A good example of that is, for example, if you're doing something like collecting data from a mobile phone based on user interaction, and that phone goes into airplane mode while the person's on an airplane, then once they get off the airplane and come out of airplane mode, and all that data flows into your analytics into Storm, and the processing time is vastly different from the time that event actually happened. It also allows you to deal with out-of-order tuples and late tuples. So late data like that airplane mode example I just gave. We also support watermarks, and watermarks allows you to specify what qualifies as late data. And we also do window state checkpointing. So the state of your windows gets stored in a database or a data store, so it can be recovered later in the event of a worker failure. So part of the windowing piece, the stateful windows, we also now support stateful bolts with automatic checkpointing. So what you see with stateful bolts looks very similar to stateless bolts. So in this case, we have a very simple topology with 2 stateful bolts and 1 stateless bolt. So as a developer, your topology doesn't really look that different. And this is, the state management API is very, very simple. Here's a simple example. In a stateful bolt, a method in your bolt called init state will be passed a key value state. And a key value state is backed by some sort of data store like Redis. And all you have to do is store that in an instance variable. And then in your execute method, you can modify that state. So in this case, we're just storing counts in the state store. So we retrieve the count from the state store, increment it, and then put it back in the state store. And behind the scenes, Storm will make sure that that state gets stored and the backing store is consistent. So automatic checkpointing. The automatic checkpointing implementation is based on asynchronous barrier snapshotting and the Chandy-Lamport algorithm. So again, what you see is spout emitting to a stateful bolt, and in that stateful bolt, you execute and update the state. Then in a stateless bolt, you just have your usual execute method. And then second stateful bolt, same thing, same sort of stateful checkpointing. What actually happens under the hood is when Storm sees a stateful bolt, it sets up the infrastructure necessary to checkpoint that state. So there's a system level checkpoint spout that will emit checkpoint tuples, and we'll emit those periodically and send them to the stateful bolts, which directs them to snapshot their state into the state store. And the checkpoint tuples pass seamlessly through stateless bolts. They're just ignored. And then, so in this case, you have one stateful bolt that will checkpoint. The checkpoint tuple will flow through the stateless bolt, and then the second stateful bolt will checkpoint its state. And then once a bolt has successfully checkpointed its state, an ACK goes back to the checkpoint spout. So the system basically knows that transaction is completed. Another new feature we've added is automatic back pressure. So prior to automatic back pressure, in earlier Storm versions, the only way to throttle topologies was to enable ACKing by setting topology spout max pending. And if you didn't require at least once guarantees, that imposed a significant penalty. I'll get to this later, but in Storm 1.0, that penalty is drastically reduced. So the way you specify, or the way automatic back pressure works is you specify in your Storm config high and low watermarks. And those are expressed as a percentage of the buffer size. And the buffer size I'm referring to is the inner worker buffers, the not 0MQ, disruptor, yep. The disruptor queues. So there's a back pressure monitor thread that monitors the buffers, and if it detects that the high water mark is reached, it will slow down all the spouts in the topology so the bolts can catch up. And if the low water mark is reached, it will stop throttling. So with this, so prior to automatic back pressure, if you had ACKing disabled, the amount of data flowing through could very easily fill up the buffers, and your topology could come to a halt. But with automatic back pressure now, it will slow down everything So your buffers stay within a reasonable level and they don't fill up and stop things. And there is, all spouts are supported by this, so since it's a system level feature, so any existing spouts will also work with the automatic back pressure feature. We also added a resource-aware scheduler. Hopefully some of you got to see the presentation yesterday on this, but what the RA scheduler allows you to do is specify the resource requirements in terms of memory and CPU for individual topology components, your spouts and bolts. For memory, you can specify both on-heap and off-heap memory requirements. If you use off-heap, it's not a common requirement, but some people do need that. For CPU, there's a point system based on number of cores, and it's kind of arbitrary. I'll talk about it a little more in the next slide, but it comes down to the fact that different CPUs have different architectures, and there's no way to really gauge the capabilities of different CPUs. Resource requirements are based on a per component instance. So parallelism matters. So when you have a parallelism of n for a bolt and you specify 100 megabytes for it, you need to take into account that that gets multiplied. So if the parallelism is 2 and you specify 100 megabytes, then you're really asking for 200 megabytes. So CPU and memory availability are described in your Storm YAML on each supervisor node. So in this example, we're specifying that the capacity for that, memory capacity for that node is about 3 gigs, and we're giving it a CPU capacity of 400. So the convention for CPU capacity is to use roughly 100 for each CPU core. So in this case, we're saying this particular node has 4 CPUs. So the way you specify resource requirements, you do it in your spout and bolts. So in this case, the first one we're saying for the spout, we want it to use 20 CPU points. And then in the next line, we're saying we want it to use 64 gigs of RAM on heap and then 16 off heap. And then it's also not necessary to set either one of them. It'll use a default value if you don't set them. So in the second case with the bolt, we're just setting a CPU value for that. One of the things some users have struggled with Storm is difficulty with debugging and monitoring topologies. So I'll go over some of the improvements we did in terms of that. Dynamic log level settings. So what this feature does is it allows you to set the log level for a running topology. So your log4j configuration, essentially. You can do that via the Storm UI and also the command line. You have an optional timeout after which those changes will be reverted. And the logs that your topology generates are also searchable from the Storm UI and the log viewer. So this is what it looks like in the Storm UI. You have a drop-down for the debug level. You get to specify your logger name, and then you can also set a timeout and then hit apply. And you can do that as many times for as many different loggers as you want. And then this is how you do it from the command line. Use the Storm set log level command, tell it which topology, the logger name, level, and timeout. Tuple sampling. How many people have ever written a put a bolt in their topology simply to log output so they know what's going on. Okay, a couple people. So what tuple sampling does is eliminate that need. So no more Trident functions or debug bolts. In Storm UI, you select a topology component, either at the topology level or individual component level, spout and bolt, and click debug. Then you specify a percentage, and that percentage is the number of tuples that are going to be sampled. Then you click on the events link in the UI, and you can view the sample log. Distributed log search is a new feature that allows you to search across all log files in a topology. So you can search in archived logs as well, and the results will include matches from all supervisor nodes. So when you submit a search, let's say you search for a specific error or exception, what it'll do is go search across all the logs, across all the topology, aggregate the results, and give you a list of everything it found throughout the cluster. And it also gives you links to the specific log file it found, so you can zero right in on the specific log file that contains the search match. Dynamic worker profiling is another really helpful debugging feature. What it allows you to do is, from the Storm UI, to request worker profile data. So you can get heap dumps, JStack output, and JProfile recordings. And then once those have been generated, you can download them directly from Storm UI and do offline analysis in whatever analysis tool you use. And you can also now restart workers directly from the Storm UI. Supervisor health checks it's not necessarily a debugging feature, but what it allows you to do is identify supervisor nodes that are in a bad state. So maybe you have one that's running out of disk space, or there's a network card issue, something's getting flaky. Health checks allow you to Storm to automatically decommission nodes that are misbehaving. And the way that's implemented is it's a simple shell script that you put in a special directory, and Storm will execute that script, and if that script returns a special value, that means that it's in a bad state, and Storm will decommission that node. So it allows you to define what constitutes an unhealthy node. Some new integrations we've introduced in Storm 1.0. We've added support for Cassandra, Solar, Elasticsearch, and MQTT. Some integration improvements. We've improved our integration with Kafka. We've introduced a new HDFS spout, so you can read data directly from HDFS and have it processed by a Storm topology. We've added Avro integration for HDFS. We've also improved our HBase and Hive integration as well. Before I forget, I want to talk about performance. Storm 1.0 is up to 16 times faster than previous versions. Realistically, you'll probably see about a 3-time improvement, and that's highly dependent on your use case and fault tolerance settings. So the 16x improvement is throughput for topologies with ACKing turned off, but that also comes into play with when ACKing's turned on. That's when you're going to get more of a 3 to 5 times speed improvement. And also that's really use case dependent, because performance really depends on what your interactions are with external systems. We also now have a 60% latency reduction. Bear in mind, performance varies widely depending on your use case. And when you see third-party benchmarks, keep in mind the origin and motivation behind those. I think there was a recent, based on the Yahoo benchmark, Flink did a benchmark where you saw it go like 100 times faster than Storm. But that was really done by removing interaction with external systems. So it was actually all happening in memory, so it's not really a realistic benchmark. The most important benchmarks are the ones that you do. Benchmark your use case and don't necessarily trust others. So what's coming up in the next Storm version? So we're continuing to release the 1.0 line with point releases for bug fixes, and then incrementing the minor version for API changes. So we're getting closer to semantic versioning. So Storm 1.1 is due out this summer, and what we've introduced in that is a revamped metrics API with a focus on user-defined metrics. So before in the Storm UI, you really only saw kind of cluster-wide metrics. Now we're incorporating the metrics that are important to you, that are part of your topology, and we're also making additional metrics available in the Storm UI. So before we just had latencies. Now you'll be able to have more in-depth knowledge of what's going on under the hood, queue sizes, that sort of thing. And then we have enhanced metrics integration, so those metrics are now exposed to Apache and Bari. So what's next for Storm in version 2.0 and beyond? We're moving away from Clojure. How many in the audience consider themselves proficient in Java? Okay, now how many are proficient in Clojure? There's one. So even though I like Clojure, moving away from Clojure allows us to broaden the potential contributor base and let more people contribute back to Apache Storm. We also received a contribution from Alibaba. What Alibaba had done was they had ported a long time ago, forked Storm and converted all the Clojure code to Java for the exact reason that I just mentioned, because their developers were uncomfortable with Clojure and they wanted to do it in Java. So they've contributed that back, and we're in the process of incorporating the new features that they bring to the table, in addition to converting our current Clojure code over to Java. One thing they didn't have was all the security enhancements that we made. So that's making things take a little bit longer, because there's a lot more Clojure code to implement the security pieces. Streaming SQL. This is currently available, but it's currently in beta. But we're adding that, and hopefully that will be production ready sometime soon. Another thing that's on our roadmap is Apache Beam integration. Apache Beam is a project that is basically the Google Dataflow API that is a unified API for dealing with both bounded being batch and unbounded being streaming, data sources with one API. So you have one API and multiple implementations that are called runners in Beam. So we're working on implementing a runner for Apache Storm. So a lot of people have been asking, how does Storm compare to Heron? Heron was originally, the benchmarks you see were originally done against a pre-Apache work-in-progress version of Storm, and that was 2 years ago. That version was 2 years old, and since then, the Apache Storm community has been doing a whole lot of work improving performance, as you can see from the previous slides. So with all the features that I've just gone over, Storm is now ahead in terms of features and largely on par with respect to performance. But Apache is about collaboration, and the Storm community is definitely committed to advancing innovation in stream processing, and there's definitely an opportunity for us to work with Heron and incorporate some of those features, but we'll see how that works out. I won't call out Ted Malaska or any other individuals by name, but there have been some people who've claimed that Storm is dead. So competitors may say so, but there are hundreds, maybe even thousands of production deployments, and we have a very vibrant and growing community that tells a very different story. So if you hear that Storm is dead, consider the source and consider the motivation behind those statements, because there could be a financial reason behind it. And with that, thank you. I've got 3 minutes for questions. If I go over that, I'm happy to move outside and continue this discussion there. Thank you. Yes.
When you are saying that when you reducing the back pressure, you are slowing down your code. Are you just starting dropping messages?
So the question is, when we're with back pressure, when we're throttling, are we dropping messages? The answer is no. So what we're doing is, when back pressure kicks in, we tell the spouts to slow down and slow down emitting. So nothing will be dropped, we're just throttling the spouts.
So the acute somewhere.
Right, so in a spout, Storm will call next tuple to tell a spout to emit the next piece of data. We slow down calling next tuple. Yes?
When will it be available in HTTP distribution?
Storm 1.0 will be available in HTTP 2.5
When will that come on?
this summer. Any other questions? Yes.
On a stateful bolt, can we have our own backing store, like for backing the key value store?
Yes. So the question is, for stateful bolts, can you have your own backing store? The state store is simply an interface, and it's dead simple. It's like the interface for HashMap. It's got get and put, and you implement that and store the key value pairs wherever you want. So right now we have one for Redis, but we're going to implement it on top of other state stores as well. And it's very easy to do, if you wanted to write one for Cassandra or something like that.
And suppose if we update that from an external source, so will it like update the back cache?
So you're talking about if you update the state outside of Storm, that's a little bit tricky. We don't have any kind of event mechanism to tell Storm that the state was changed externally. So no, not yet. But it's possible, but it would make the interface a little more difficult to implement. Yes.
What are the improvements in terms of Kafka integration?
Kafka integration, we're moving up to versions, to newer versions of Kafka. We have a separate, we're still working on it, but we have a separate Kafka integration component that uses the new consumer and producer APIs. And there are also some stability and bug fixes in there. Got about 12 seconds, so I'm going to stop and I'll move outside if anyone else has any questions or wants to talk to me. Thanks again.